Compound semiconductors like gallium arsenide and indium phosphide are replacing silicon in high-frequency and optoelectronic applications. These technologies depend entirely on ultra-high-purity metallic arsenic refined to 7N and 8N grades. The upstream supply chain for this material is highly consolidated. China controls 120.0 metric tons per annum of refining capacity. This represents 92.3% of the global total. Alternative capacity is fragmented across Japan and Germany. The United States possesses zero domestic primary refining capacity for 8N arsenic. This creates a single point of failure vulnerability for Western defense systems and telecommunications infrastructure. Global demand for high-purity arsenic is accelerating. Total consumption expanded from 71.8 metric tons in 2019 to an estimated 118.7 metric tons in 2024. This represents a compound annual growth rate of 10.6%. Radio frequency microelectronics remain the primary volume driver. Gallium arsenide power amplifiers for 5G and 6G infrastructure consumed over 57% of total supply in 2024. Simultaneously, high-growth optoelectronic applications are expanding at 12.6% annually. These include indium phosphide laser diodes for fiber optic networks and vertical cavity surface-emitting lasers for automotive LiDAR. This demand surge intensifies the geopolitical risk of the refined material bottleneck. The high concentration of refining capacity is sustained by severe technical barriers. Transitioning from crude smelter byproducts to semiconductor-grade metal requires a complex four-stage thermal and chemical process. The cumulative material yield of this process is only 9.6%. Purification must reduce critical impurities like sulfur and silicon to subparts per billion levels. The highest 8N grade requires transition metal concentrations below 10 parts per trillion. The highly toxic nature of arsenic vapor processing imposes strict environmental and regulatory constraints. These physical and chemical realities prevent rapid capital deployment from establishing alternative refining capacity. The bottleneck is structural and cannot be bypassed quickly.